very much. So before Alain takes over with more details about, let's say, a case study on computations of real integers, talking about more interesting details of the informal and formal lean aspects of it. I want to quickly first tell you a little bit about motivation. Why do we care about these computations? Actually, what kind of computations do we care about? And also introduce the basic objects that will appear in the case study. So these are number fields, and I was pleasantly surprised to already see number fields appear in some example 2 talks ago, and the word Dahmen, I'm a big fan of that. And hopefully at the end we'll see how much time I have, because I should allow Alain enough time for the most interesting part. Maybe I'll also introduce some basic example how you could set up some data type in Lean, but we'll see if we get there. So I'm a number theorist. So you can say, okay, what is it about? Well, okay, study of the integers in its most basic setting maybe, and then you can generalize a lot, of course, and do arithmetic geometry and whatnot. And of course, there's lots of beautiful, let's say, pure theory. Or maybe it could. Okay, so I'm going to be informal about what I mean by computation, right? But maybe in practice it is something where you something that you cannot do as a one-liner on paper, or as a few rewrites in a proof assistant, but something where you would normally have the help of some computer algebra system, or maybe you've written your own code in C or whatever to do some long deduction. So you can do a lot of beautiful theory in number theory, but surprisingly often, I think you actually also need computations, longer computations. That could be the case because you actually just study a very explicit problem, and then you could say, well, I mean, this is such an explicit problem, of course you need explicit methods and computations. But actually it also appears in let's say, more theoretical statements. If you, for example, want to generalize a modularity statement, that if the curve of Q is modular to, let's say, some specific real totally real number fields, then it turns out that the only way we know currently how to do that is, by using lots of heavy theory and actually computing, with certain modular curves, the so-called k-rational points. And the only way we know how to do that is by doing really some crazy elaborate computations using periodic integrals and other kind of heavy, completely non-trivial computation. So I think that's fun to note that even if you're like a purist, for some of the very interesting theorems, you still need computations. Well, as far as we know, maybe somebody at some point comes up with, here I have a pure proof, and then would also be happy. It would be beautiful. Okay, so how do you do your computations? Well, of course, you could use your favorite computer algebra system. If you're a number theorist, maybe you like Magma or Chavarri or Sage, or you might even use Maple or Mathematica, or you write your own code in C or your other favorite language. And that's perfectly fine, but up to some degree, right? I mean, maybe you trust it, maybe you don't. Maybe it's a bit informal, those computations, because sometimes it's not even clear what the specifications are. If Mathematica says, I compute this integral, it might not even be clear, like, did you take a branch cut somewhere? So if you have that in a formal setting, not only provides it, a more trustworthiness, but it's also, actually, the specification is linked to the theory, right? Maybe you get the theory, you might still get sort of the theory wrong in your proof assistant, but at least it coincides. So if it implies something clean, then there you go. So the aim is not to build a computer algebra system inside a formal setting. I mean, that would be beautiful to have, but that's of course an old dream that would be a gigantic research project. So we aim at just verifying some fragment inside a theory prover and connect it up with the theory, and then maybe apply it to solve some explicit number theoretic problems. So I guess it's I've also talked to Becca a bit. It sounds a bit maybe similar. Well, okay, maybe from the database point of view to what you can do with graphs. And of course, it's also not, the idea is, let's say, not new, but surprisingly little has been done if you look at sort of non-trivial number theory. Yeah, so okay, I want to connect this with the workshop, right? Because it's a bit of a different theme than maybe most of the talks. Now I'm bridging computations, which I claim are very informal, right? Well, sometimes they're really informal if you read a text. You say, oh yeah, by some computation, or I read, yeah, by writing some Sage script, it follows. And then, okay. I mean, yeah, connected to formalization. And then I guess this is also maybe a recurring theme. Whenever possible, I mean, these computer algebra systems, I love them. I think they're great. And I don't want to, yeah, redo everything, re-implement the algorithms in some proof assistance and improve their correctness. I mean, that would be very nice to do, but it will be maybe unnecessary if there are some nice certificates around. So if the output of the computer algebra system could be verified inside your proof assistant. And it's funny because, well, I understood that maybe in the graph setting there is, well, maybe somewhat more about certificates now. But in number theory, well, for very basic objects like prime certificates, of course, composite certificates, or irreducibility of polynomials over Q or so, there has been quite some research into certificates. But the moment you step it up a little bit and go to slightly more advanced number theoretic objects, well, as far as I'm aware, if I'm wrong, please tell me, there are basically no certificates around. Well, I mean, other than the algorithm. If I ask, oh, but how do I certify this, that this is the ring of integers? Then people say, well, there's an algorithm. The algorithm is the certificate. Okay, yeah, that's correct, but I want something easier, right? So part of the research question is also for, let's say, the slightly or much more, let's say, advanced or deep mathematical objects. Can you come up with a more reasonable certificate and then, well, still run your computer algebra system and let it just output a little bit more so that you can verify it. And I'm okay with, I mean, if it's a beautiful certificate that tells me something, I would be very happy. But if it cannot come up with something, then it's also very fine if it's a very long, verbose, a very non-human readable certificate. Well, as long as you can compute with it and reason with it in the proof assistant, right? Because if it's very tedious, I mean, that's where these things are good at, so you should consider those. And so the original motivation is really, let's say, to solve problems in number theory, where I see computations popping up. But if we actually build this infrastructure, then you can also say, well, hey, I guess this has also been mentioned before, there are databases like the famous L function and the form database in number theory. If you can actually do these computations, then why not try and formally verify some of the entries? As far as I'm aware of, basically no non-trivial data of the LMFTB has been formally verified so far. Okay. Yeah, maybe I should also say that we're going to do this in Lean, also in other systems already, let's say in Coq, or maybe I should say ROC now. This has been explored. For example, Sia Mapubi and co-author have proved the Appearance original, formalized Appearance original proof of the irrationality of CDA3 by having some Maple script output some certificates for some recurrences that occur in proof. And also it would be nice if it's automated, if you, let's say, do it in Lean or whatever proof assistant, that there's a call to, let's say, some computer algebra system that will then import a certificate. And this is, I mean, basic examples of that is also around. For example, polyarithmetic in Lean, which is a generalization of the linear arithmetic. Basically, it helps you to certify non-linear polynomial identities by making a call to SageMath, and then finding some linear combination there, which would be the certificate that you could then certify in Lean. Okay. Now, I'm already talking too much, so these nice slides with topology, I'm going to skip. Of course, the number theory is connected to geometry and everything. And then the first, the point of this slide is that really actually solve, and you can have nice theory, so see Gauss and Popper theory are about finiteness statements. If you have basically a two-variable polynomial, and you want to ask what are its integer solutions or what are its rational solutions. For example, you write something in x and y, say, okay, this equals 0, solve it in rationals x and y. That turns out to be surprisingly hard already. So one variable is fine over z or q, but the moment you have two variables, it becomes extremely complicated already. We might not be in the Hilbert-10 fragment, or maybe there's some hope that there actually do exist algorithms for deciding this, and or if this is empty or not, and the integer solutions, and if it's not empty, maybe even finding everything, if there are finitely many. But so far, all the proofs that let's say, show finiteness in certain cases are, well, in general, ineffective. Of course, there are families where you can do stuff. In general, all known proofs are ineffective in the general situation. Which means that we have a lot of work to do, huh? And it's actually, I would say that solving, finding integer or rational solutions to two variable polynomials over the integers is actually a big research theme in computational number theory. And as I said before, it has a nice applications in pure mathematics. And here's a well-known example. I think it has been mentioned already a few times by Catherine Pleasant or by Jennifer herself. I think it would make a really cool formalization project, also a really hard one, because basically none of the basics where it builds on, it has to build on is there in the computational setting, and also in the theoretical setting. But you have the curve, so some degree 4 two-variable polynomial. Okay, find all rational solutions. Very explicit. Turns out it has 4 solutions. Yeah, and I couldn't resist saying, oh yeah, with 3 more rational points at infinity, but actually, you should see this, write down the projective model, and then you have 3 more points, blah, 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 blah. But yeah, this is just for my own sanity that I should say that, right? So you can forget about that. I mean, this is a true statement. The rational solutions are, this is just the notation for the rational solutions. It's just this. And this has applications for statements about surjectivity of Galois representations associated to elliptic curves. And other, modular curves have other nice implications in theory. Okay, so let's take many steps back and do something more easy, more basic. So fix some non-zero integer g and consider so-called Mordell equation. So a square and a cube, when is their difference g, right? Solve it in integers. Y squared equals x cubed plus d. So this is actually a fragment where effective resolution methods are known, and in literature this is solved for up to some large absolute value of d. So as a previous case study with Dahmen, Alain and Ivana Coppola, myself, we said, okay, let's try to solve these things in Lie, in 3 at the time, for a handful of values of d, minus 1, minus 2, minus 5, minus 6, minus 13. We took them negative to make our life easier. But in principle, some more work could also be done for many other values. And then, for example, you have a statement on D13, like, okay, for integers x and y, the equation y squared equals x cubed minus 13. There's a solution, and x must be 17. Of course, you can also phrase it in different ways. X has to be 17, and y has to be plus or minus 70, but the y value will follow easily if you know the x value. There's a sorry here, but we formalize this. And there's a very explicit basic statement about the integers, but we really had to set up arithmetic of the number field q squared of d for these cases. So this is an example of a number field. It's let's say all elements from a plus b squared of d, where a and b are rational numbers. And that's because it's nice to put the d on the other side and factor, and then d has to be a square, and d is not a square for these d, so you just make it a square. Yeah, that's what we do. Okay, we join the square root of d, then d is a square. Why not? But then you're outside of q and z, and you have to deal with all kinds of subtleties. What is the so-called ring of integers here? What turns out to be z squared of d? What is the class group, meaning that these rings of integers need not have unique factorization in elements anymore. It might not be a u of d. So you need to compute how far is it from being a u of d. And then you can still work with unique factorization of ideals, but then you have to do computations with ideals. So we set it up in the setting, and it actually worked, and we applied it to some explicit equations of this shape. But of course, for more general divergent equations, you don't want to stay in this quadratic setting, and actually, I would say that number fields, so the generalization to this to a higher degree, is not just necessary for direct integration, but for almost any number theory. So we consider number fields, higher dimensional generalization of this, and we want to compute basic invariants, like the ring of integers. I'll tell you exactly what it is, which is the focus of the case study that Alain will talk about. And other things would also be nice, class group, units groups, etc. But in order to do these other things, you first need to get your hands on this. So I quickly want to introduce the basic objects. So with a number field, it's a finite field extension of Q, where finite means it's a finite degree of a Q. So if you have a field extension of Q, then it's actually, if you forget about most of the multiplication, you just remember the scalar multiplication with elements of Q and its addition, then it has a structure of a vector space. Vector space has a dimension, and then this degree is of the number field is just, well, degree of an extension of Q is just the dimension as a vector space over Q. And having finite degree, this means that as a vector space over Q, it's finite dimensional. And so the degree 1 number field is just Q itself. Then, well, we have some examples of degree 2 number fields that we already saw. Qi, all elements from A plus Bi, with A being Q, or I is the square root of -1, Q square root of 5, all elements of the form A plus B square root of 5, with coefficients A and B and Q. But then you can go higher. This take a cubic polynomial. This is an irreducible polynomial over Q. I take any root. Actually, you don't really have to compute a root, but for sake of sort of concreteness, let's say we take a root in the complex numbers. And then we just look at all linear combinations of 1, theta, theta square, where the coefficients are rational numbers. And that's a number field of degree 3. And actually, it's just isomorphic to Qx, the polynomials in Q, modulo G. So this is just also a way to compute with it. You have a generator, and you have a relation, G of x equals 0. You join x, and then have a cubic relation. Every time you see x cubed, you can replace it with minus that. And this actually generalizes. You can just take any irreducible polynomial in over Q. Well, for sake of concreteness, take a root, but actually you don't really need to do it. And then look at linear combination of 1 t theta squared up to theta to the n minus 1, or n is the degree Q linear combinations, and that would be a number field of degree n. And it's just actually the same thing. It's just polynomials in Q modulo f. You have the generator, and f you basically is, well, this is the image of x in this quotient is a root of f. And all number fields occur in this way. When primitive element, any number field is of this shape, meaning any number field is isomorphic to something of that form. And then the ring of integers, and probably I should already stop. So that's what Alain will talk about. It's a very important invariant of a number ring, where, well, as I said, all kinds of other computation what to do will follow from. So it's defined by, well, you can see it as a subring of a number field, and it consists of all elements that are 0 for some monic polynomial f with integer coefficients. So if an element satisfies, is a 0 of a polynomial with leading coefficient 1, monic, and integer coefficients, then it's an algebraic integer. And it's maybe not clear from the definition immediately that it is a ring, but it is a ring. Nice structure. An example, the ring of integers of Q is a Z. So basically it just generalizes how Z sits inside Q as a nice arithmetic ring where you can do factorization, etc. And the ring of integers of Qi is just the Gaussian integers, Zi, elements of the form A plus Bi with A, B, and Z. But then if you do the ring of integers of Q squared root of 5, you don't get Z squared root of 5, but you get something larger, Z, the golden ratio. That's because this element should be in the ring of integers because it satisfies, I think, x squared minus x minus 1, which is a polynomial with leading coefficient 1 and integer coefficient. So it should be, by definition, it's inside here, and it turns out to generate this ring. Yeah? So all integer linear combination of 1 and the golden ratio would be the ring of integers here. But things can become more complicated quickly. So, for example, if you take this cubic polynomial we had before, then you take a root, then the ring of integers turns out to be integer linear combinations of 1 theta and theta plus theta squared over 2. Of course, you have many different ways of writing it down. You can do all kind of base transformations, but the point is, you can never find one element such that this is Z adjoins something. And so, meaning it's not monogenic, it's not generated by one element over Z. But luckily, so it's more complicated than the number fields case, which is always monogenic. can just say this is the number field is of the form Q adjoin one element. And the ring of integers might not be of the form Z adjoin one element. But luckily it still has, well, it's a Z module of, free Z module of rank N, which means that the ring of integers inside a number field of degree N has a Z basis, also called an integral basis, meaning you can pick at least N elements in OK, such that this ring consists of all integer linear combinations of your base elements, and that combination is actually unique. So if you want to set up some data type, you can always say, well, okay, the ring of integers can be expressed as just Z to the N with coefficient-wise, coordinate-wise addition, and multiplication, okay, more involved, but at least that's the basic type. Okay, so now I think in view of time I should probably skip this, because you will tell people in general how this works. So this is an example how you could set up some basic stuff in the quadratic case. Maybe the most important thing is to point out that, well, okay, you just say it's pairs of elements, you have addition, and the multiplication is just specified, completely determined by what it does on basis elements. So in this case, in the quadratic ring, you have always two elements, 1 and theta. Well, these are obvious, and then you have to say what theta squared is. It's a plus b theta, because this was my polynomial. Okay, then you can do computations with it. But before I finally hand over the floor to Alain, maybe also say one quick word about LMFDB. So, maybe many of you already seen this. So it contains lots of interesting things. If you want to go for low-hanging fruit, maybe Dirichlet characters. Maybe that's the one thing that should be really easy. I think the rest is slightly hard up to very hard. You need to get the definitions inside the formal setting. Okay, for number fields, the definition is not so hard, but the computations are. And then you can say, okay, I want all degree 5 number fields whose discriminants prime divisors are contained in 2, 3, and 5, and maybe it should not be monogenic, so this should be sort of complicated. Then you get the list of 442 matches, and you get polynomials with degree 5 defining the number field. You can click on them, and then, for example, it also gives you some integral basis. And if you've forgotten what it is, you can click on it. It tells you an integral basis, blah blah blah. And in terms of the generator, it just gives you some integral basis. So that's basically what we aim to verify. I must say this is still work in progress. So we're already happy. I mean, if we can do, let's say, if we take one big entry and verify it. I mean, we're not at a stage yet where we can say, oh, we're really importing lots of stuff, but at this point, it's really hard enough to verify isolated things. But for example, all of the polynomials, 140 polynomials in this list, we can do something with. And I think it's now time for Alain.
It's in the same computer or different?
No. It's, okay. You want this?
So what's the coverage you have for this import of LMFDB to Lean or?
So at this point we're really just like we're just copying it, right? So really just looking at, okay, can we actually do large entries? Can we just copy basic stuff? So at some point,
It will be a bulk import.
Okay, so I'm going to talk about the case study where we try to verify rings of integers in Lean, and good thing that Sander already introduced the concept of ring of integers. So the basic goal is, suppose you have a subring of a number field that you're told is a ring of integers. So perhaps you computed a Z basis with Sage. How can you obtain a formal proof that this subring is indeed the ring of integers? So in Lean terms, you have something of type Z subalgebra. You think of this as a subring, and we want to prove this equality. O is the integral closure of Z in K, and the integral closure is precisely what Sander described as the elements that satisfy a polynomial that is monic in the integers. So we have that a number field is isomorphic to the polynomials in Q modulo some defining polynomial. So if we want to compute in K, we need to compute modulo a polynomial. So this is the first step that we have to overcome. And well, the thing is, mathlib polynomials are not very suitable for computation. So we want to have a different way to represent polynomials that are better for our purposes. And for this, there are essentially two ways of doing it. So either the dense representation of polynomials, which is just the list of the coefficients, and the sparse representation, which you only store the list of monomials. And so there was a work group 2 weeks ago working on implementing sparse polynomials in Lean. But for our purposes, we used a dense representation for polynomials because we don't really deal right now with the very big degree polynomials, and we have no reason to expect them to be sparse. What we do is we will define polynomials as just the list of the coefficients. And so we have a map that goes from, so R is a semi-ring, you can take it to be a semi-ring, and we have a map that goes from lists in R to the mathlib polynomials, which basically maps the list to the corresponding coefficient, polynomial with those coefficients, where the last entry is mapped to the leading term.
That will just come back.
Just
Okay.
leave it because it will come back. By and large, it does.
Yes. Okay, so we defined computable polynomials as lists in R that have this property that they are equal to themselves when you drop the trailing zeros. So this function drop trailing zeros drops the trailing zeros, and so this is similar to polynomials in the mathematical component library for Coq, but it differs in the case that R is a trivial ring. And we do have this isomorphism of computable polynomials is isomorphic to the mathlib polynomials. And usually we only need the forward direction for our purposes. So now I told you about how we are dealing with polynomials, but now how do we compute inside O? So the way we're going to do it is with our multiplication table. So we have the number field which you obtain adjoining a root of f, theta is called, and we have a z basis. So the wi's are going to be a z basis for our ring O. So you see, every element in O is just a linear combination of the elements in the basis. So the multiplication of two elements in O is completely determined by the pairwise multiplication of the elements in the z basis. So completely determined by this. So our first aim is, if we are given a z basis, how do we construct the corresponding subring in Lean, and how do we obtain a proof of the multiplication table of this subring? And in order to do this, we're going to represent the elements in O as vectors in Zn. So Sander already mentioned this, that we can just look at, if we take an element in O, we can look at its coordinates with respect to the Z basis, and then we can represent this element as a vector. Will it come back?
Yeah.
Okay.
Oh, maybe touch something.
We all cross our fingers.
Yeah, so, and we want to generate a term times table automatically. And this term times table is essentially consists of a basis, a Z basis in our case, for our ring, the table itself, and a proof of correctness of the table. And we want to generate this proof of correctness automatically. And the way we're going to do this is we're going to use our polynomial arithmetic. So we can write every element in the Z basis as a polynomial in Q evaluated at this theta. And so the multiplication of these two elements in the basis, being equal to this linear combination is precisely equivalent to this polynomial, a polynomial existing such that this identity is satisfied. So this polynomial identity is satisfied. So we can verify a multiplication table by providing the certifying polynomials Sij and just checking all of these polynomial equalities. And for this, we can collect this data in a structure that we call the subalgebra builder. And so it consists, well, part of its fields is the polynomials bi, which correspond to the z basis, the multiplication table of O, and the certifying polynomials Sij, together with the proof of all of these polynomial identities, so all of this. But the thing is, all of these identities are proven automatically. It's just by decidability, because our operations in this are computable, and we have decidable equality in the integers, so everything is fine. We can do this automatically, and once we have this, we can compute in O, because multiplication in O is just depends on the multiplication table, and addition is just pairwise addition of the coordinates. So this is an example. I have this number field, which I obtained by adjoining a root of this polynomial. This is a ring of integers, and this is a subalgebra builder. So in B, I am giving the z basis, well, the polynomials corresponding to the z basis. You have to divide them by 2, because I'm using a common denominator here. But this B corresponds to the polynomials bi. And then A corresponds to the multiplication table, and then S is the certifying polynomials for this multiplication table. And
Back.
okay.
This one.
This is good to keep things interesting.
It does.
Yeah, but all the proofs are by design, as you can see. Okay, now that I told you how to compute with polynomials and how to compute in O, I'm gonna tell you briefly how to verify the ring of integers. So to verify the ring of integers, you can do it locally. So you can prove that it's P maximal, whatever that means, for every prime P. And what it boils down to is proving that the kernel of some linear map, it looks a bit scary, but it's fine, no worries. You only need to know that it's a linear map. Proving that the kernel of this linear map is trivial shows that this thing is P maximal. So if we can certify the triviality of this kernel, then we're, for every prime P, we're done. And we also have Dedekind's criterion, which reduces our task to only proving P maximality in finitely many primes. So what we did is, so if you have a polynomial over the integers that is irreducible and monic, I wrote a script that will generate a .lin file, and it will construct this automatically, this subring O, and it will generate a proof that O is indeed the ring of integers of K. And so for all of this certifying data, we're using Sage Math to generate it. And with this, we verified the ring of integers of the list that Sander showed. So 142 number fields, we verified the ring of integers. And just very quickly, I will show you an example. So if you give the polynomial to this program, it generates this file, and it's essentially, well, you have the defining polynomial here, and then this is the z basis that I'm constructing with this subalgebra builder. So the z basis is given here. You divide these polynomials by 24 because this is a common denominator, and you get this basis. This is a multiplication table, the certifying polynomials, and then this constructs the corresponding subring, and together with a proof of the times table. So the times table here, I obtained something of type times table, and if you recall, the times table has the proof of correctness of the times table. And so I told you that you only need to prove p maximality for a finite number of primes, and in this case, you only need to prove p maximality for these primes. Debyekin's criterion gives us an easy way to verify p maximality for some of the primes, but for other primes, we need to use the certificate based on Post and Sassenhaus. So, for example, this is proving 2 maximality. And I'm giving a bunch of data, and just all of the proofs are by decide. So this is essentially checking a bunch of identities that are happening in O and in O modulo P. And here similarly for 3. And you end up with a proof that O is indeed the integral closure of Z in K. And so just to finalize, let me tell you some conclusion. For the example that I showed, the proof that f, the polynomial, is irreducible is done, and we have ways to certify irreducibility of polynomials for, in some sense, most polynomials, but still we're working on more certificates for irreducibility of polynomials. So the script will output everything sorry-free except perhaps a proof that f is irreducible. But yeah, so this are
You
some...
should point out that in this list, that irreducibility is okay.
Yeah. And these are some first steps toward bridging the gap, as Sander mentioned, between computer algebra systems and ITPs. And this work in progress. So right now we're using the Z bases that Sage gives me, but we want to match it up with the integral bases that LMFDB has, so we can verify these entries and also verify the discriminant of K. And well, the natural question is how far can we take this? How much can we verify, and how big the degree that we can deal with? And well, this work, having a proof of the ring of integers is essential for possible future work, which is certification of prime ideals and something called class group computations, and eventually applications to solving Diophantine equations. Thank you.
Thank you.